All right, so let's see some more examples of indeterminate forms. So here's one. So first, let's decide what we're looking at here. I've got the limit as x goes to 0 from the right of 1 over x minus 1 over arctan x. So let me draw a couple of real quick sketches here. This is a quick sketch of 1 over x. And x is going to 0 from the right, so I'm looking at this part of the graph, and this is the vertical asymptote. So I would say that 1 over x is going to positive infinity. Let's talk about this other part. I am not too familiar with 1 over arctan. However, let me just draw arctan. And I'm going to go into maybe a little more detail than I strictly need for this. Arctan has two horizontal asymptotes. And it goes kind of like this. But we're not really interested in the asymptotes for this. We're interested in when x goes to 0 from the right. So arctan of 0 is 0, and as x goes to 0 from the right, this is coming in from above. So I would say 1 over arctan. Since arctan is going to 0 from above, it's like 1 over a small positive number, so I would say this is also positive infinity. I'm ignoring the negative sign in front. So, of course, with this negative sign, I would call what we're looking at infinity minus infinity. That's what we're looking at here. This is an infinity minus infinity form. So this is one of the weirder indeterminate forms in the sense that there's no standard way to approach these where it's just automatically going to lead you to L'Hopital's rule. The best advice I can give is to use some kind of algebra to deal with it. And the details are whatever they are, and every problem is different. And one I notice about this one is that I've got a fraction minus another fraction. So what's something that we often do? We get a common denominator. That's an idea. Oops. 0 from the right. Okay, so my common denominator is going to be x arctan x, and to get that I would have to multiply the top and bottom of this by arctan, so I'm going to get arctan x, and I would have to multiply the top and bottom of this by x. So there we go, I got a common denominator. All right, let's start over. Look at this again. So, as we discussed, arctan is going to 0, like arctan of 0 is 0. So this is going to 0. Of course, x is going to 0. So I would say the whole top is going to 0. Also on the bottom, well, x is going to 0 and arctan x is going to 0. So I've just got a big 0 on the bottom. So I would call this now a 0 over 0 form. And just like that, it's something that we can apply L'Hopital's rule directly to. So let's go. Derivative of the top. Derivative of arctan is 1 over 1 plus x squared. Derivative of x is 1. On the bottom, I've got a little product rule, so derivative of x is 1. And then I'll do x times the derivative of arctan, like that. Okay. Now I've got a new limit to deal with, and before I sort of look at this and try to tell what's going on with it, maybe I should clean it up a little bit. One thing that I don't like is fractions inside of my fractions. So what I mean is I have this big fraction, like this big fraction bar right here. But if I look on the top, I see this little fraction, and also if I look at the bottom, I see this little fraction. I don't like that. Those are fractions inside of my fractions. Fractions are bad enough without fractions inside of them. I am going to multiply the top and bottom by 1 plus x squared, because that should kill this bottom and this bottom. So we distribute. When this goes here, of course I just get 1. When this goes here, I get, well, 1 times anything is itself. And I'm going to be careful and use parentheses because this minus distributes to the whole thing. And let me distribute that here. So I'm going to have a 1 plus x squared arctan x plus, and this times this just goes away, and I just get the x. Okay. Let me just clean this up a wee bit more just because these ones cancel. So not a whole lot is going to happen in this step. That's the only thing that's going to happen. There we are. Sorry. Okay. So now that I've cleaned this up, let's look at it again and evaluate it. Maybe it's possible to just tell the answer now. Well, the top is going to 0 because x is going to 0. So the top is going to 0. On the bottom, well, this is going to 1, but it's multiplied by arctan, which is going to 0. So I would say this whole thing, that's like 1 times 0. So I would say this whole thing's going to 0. Of course, x is also going to 0. So it looks like I still have a 0 over 0 form, which justifies using L'Hopital's rule again. Okay, negative 2x is the derivative of that. Now I've got another little product rule. So I am going to have 1 plus x squared times the derivative of arctan, which is 1 over 1 plus x squared, plus derivative of this is 2x arctan x plus this, which is 1. Okay, let me clean it up before I try to figure out what's going on here. The most obvious thing first is that those two things cancel, and this leaves a 1, right? So top is minus 2x, and the bottom, so let me take this 1 and put it with this 1 and call this 2 plus 2x arctan x. And now let's try to figure out what's going on here. We need to know, is this still an indeterminate form, or can I just look at this and tell the answer? Well, the top is going to 0. The bottom, so this is just a 2, and this part, well, x is going to 0 and arctan x is going to 0, so this is definitely going to 0. But I've still got a 2 on the bottom, so basically I would say this is, I just see a 0 over 2 plus 0, which is not an indeterminate form. That is just 0. Let's take a look at this one. What makes this one scary to begin with is, first of all, I just have a power to another power. Like, it's hard to even look at. I've got x, and x is raised to the power e to the negative x. So what are we looking at here? I'm going to guess that this is one of those indeterminate forms involving powers like 1 to the infinity or infinity to the 0 or something like that. And so how do I break this down? Let me look at the very bottom. So x is going to infinity, so this is definitely going to infinity. And then let me put another circle around this whole thing, the e to the negative x. So let me just draw another quick sketch. Here's my mental image of y equals e to the x. That's not e to the negative x, that's just e to the x. Of course, e to the negative x would just be like flipped sideways, but this is what I remember. So what we're dealing with here, x is going to infinity, and I'm looking at e to the negative x, so roughly speaking, I'm looking at e to the negative infinity. So I'm thinking about the part of this graph that goes far to the left, and this is the horizontal asymptote. So I would, roughly speaking, e to the negative infinity is 0. So this is going to 0. So sure enough, what we have is an infinity to the 0 form. So what do we do with these? Let me sneak an L in there. So I'm going to call this limit L. I'm going to do the natural log of both sides. And I can write the natural log inside of the limit. That's the trick. And the reason why we do that is because we like to use a log rule. So I have to be careful here because there's so many powers. What I'm allowed to do is if I have a power on the inside of my natural log, I can take that power down. And what that means is I'm going to take this entire thing down. Like that's the power on top of the x. Okay, and that should transform this into a different type of indeterminate form. So once again, we already said this, e to the negative x, that's going to 0. As x goes to infinity, that goes to 0. What happens with ln x? Well, here's my mental image of ln x. Of course, it's actually just e to the x and ln x are inverses. So this graph, if I draw the line y equals x and reflect it, then I get this graph. That's one way to remember it. So this horizontal asymptote turns into this vertical asymptote when we do that. And, well, but x is going to infinity. And one thing to remember about ln x, which actually maybe this picture isn't even that helpful and perhaps even deceptive. As x goes to infinity, natural log x goes to infinity. And when I say this graph might be deceptive, it's because I'm thinking of the far right part of this graph, and it's not really clear what's happening. From this picture, I can see that it's starting to flatten out, and that is the case. As I go farther to the right, it's going to look like it's flattening out more and more, which might lead one to believe that there's a horizontal asymptote. There might be some horizontal line where this graph just never goes above that line, but that isn't the case. It does go up forever. Like as I go far enough to the right, this will go above whatever level you like. You can draw a horizontal line at like 1,000,000 or 1,000,000,000, and if you go far enough to the right, it will go above that line, no matter how high you draw it. It will take a long time because this does it goes to infinity very slowly, we say. Anyway, that's something to remember. As x goes to infinity, ln x does go to infinity. So we are looking at a 0 times infinity form. What do we do with those? Typically, I just pick one of these and stick it on the bottom. I see a negative power here, so that's like really begging me to stick it on the bottom. So let me call this an e to the x on the bottom. And okay, what are we looking at now? Well, this is going to infinity, like we said. Now that I'm talking about e to the x and not e to the negative x, now I'm thinking about this same graph over here, but I'm looking at the far right part, which this is infinity. So I am looking at an infinity over infinity form. Finally, that's something that we can apply L'Hopital's rule directly to. Great, let's do it. Derivative of this is 1 over x. Derivative of this is e to the x. I do not like fractions in my fractions, so let me fix it. I'm going to multiply the top and bottom by x. So on the top, this is now just 1. And on the bottom, it's x e to the x. Okay, so what are we looking at now? The top is just 1. It's not going to infinity or 0 or anything like that. It's just 1. What's happening on the bottom? Well, I'm multiplying two things together. This one is going to infinity. This one is also going to infinity. Infinity times infinity is not an indeterminate form. If you take a function that's going to infinity times another function that's going to infinity, it's like, what do you get if you take a huge number times another huge number? You get an even huger number. So roughly speaking, if I see infinity times infinity, I just say that's infinity. So the top is just 1, and this bottom is going to infinity, so I would say this limit is just 0. Great. Let's do one more. As x goes to infinity, we're doing x minus ln x. So x is going to infinity. As we just discussed a minute ago, I don't need to draw the graph again. As x goes to infinity, ln x goes to infinity. So we are looking at an infinity minus infinity form. And while last time we had one like this a minute ago, they were fractions and we got a common denominator, but these aren't fractions. I'm going to do something else. And so what I'm going to do here, this, like the motivation for this requires a little bit of intuition. So let me actually bring back this graph, the one I just drew of y equals ln x, and bring it back to this discussion of as I go farther and farther to the right, this does go to infinity, but it goes to infinity very slowly. If you zoom out, it almost looks like it has a horizontal asymptote, but it just never quite levels off completely. It keeps going as you go farther to the right. It keeps going up and up and up, just slower and slower. Meanwhile, the graph of x keeps going up at a constant rate. It's just a 45-degree angle. So what I'm describing, the intuition is that I think that as x goes to infinity, x is much larger than ln x. So this is not a formal statement. We're going to justify everything we do, but this is what's motivating what I'm going to try. So what I'm going to try is I'm going to pull out whichever one's bigger. We think that x is much bigger than the other one, so what happens if I pull out an x? I get 1 minus, and this doesn't have an x, so I'm just going to write that. So that's the same thing. And so what I have here is, now that I factored this out, this is of course going to infinity. And what do I have in here? I've got a 1 minus, okay, now what are we looking at here? This is technically an infinity over infinity form, like this part that I circled in red. Because ln x is going to infinity, x is going to infinity. So I would say this is an infinity over infinity form. However, we suspect, based on our intuition, we suspect that the top of this fraction is much smaller than the bottom of the fraction. So let me give you a preview, and this isn't justified yet. A preview of what's about to happen is this is going to go to 0 because the top is much smaller than the bottom. And if we trust that, then that means when I look at this whole set of parentheses, this is basically 1. So I'm taking 1 minus essentially 0. And then I zoom out again and say, well, if this is going to infinity and the thing in parentheses is going to 1, then probably the answer is going to be infinity. Let's justify that. So I claim, or, well, let me not even state this as a claim. Let's say, let's find this. So this is a pretty easy L'Hopital's rule. As we discussed, this is an infinity over infinity form. So we can directly apply L'Hopital's rule. Derivative of the top is 1 over x, derivative of the bottom is 1. And as x goes to infinity, this goes to 0. That's what we expected. When we were looking at this, we said, well, the top is much smaller than the bottom, so we think this is going to 0. Therefore, when I rewrite the big limit, once again, this is going to infinity. This whole part, we are now fully justified saying this is going to 1. And this is no longer an indeterminate form now that we figured out that this is going to 1. Look at the big picture. I've got something going to positive infinity times something that's going to 1. This is going to be infinity, which is what we guessed a minute ago.